The washer method. In this video, we use definite integrals to find volumes of three-dimensional solids by using the washer method. The washer method is an extension of the disk method to find the volume of a solid of revolution that has a cavity in the middle. Firstly, let's remind ourselves how we would calculate the area of a ring or a washer in geometry. A ring or a washer is a combination of two circles, one inside the other. So we have to deal with two radii and hence find areas of both circles. Then subtract the area of the smaller circle from the larger one to get the area between both circles, which is actually the area of the ring or washer. We can do the same thing for finding the volume of a solid of revolution that has a cavity in the middle. Thanks in advance for watching this video. If you like this video, don't forget to like and subscribe to the channel and activate the bell. It's very important for the continuity of this channel. When the solid of revolution has a cavity in the middle, the slices used to approximate the volume are not discs, but washers. Washers are discs with holes in the center. For example, consider the region bounded above by the graph of the function f of x and below by the graph of the function g of x over the interval from a to b, where f of x is greater than g of x. When this region is revolved around the x-axis, the result is a solid with a cavity in the middle, and the slices are washers. You should notice that f of x and g of x represent the outer and inner radii of the washer. The cross-section is a washer. We find the area of the washer by subtracting the area of the inner disk from the area of the outer disk. The volume of the solid of revolution is the integral of this cross-sectional area. Consider the region R between two curves f of x and g of x, such that f of x is greater than g of x, for an interval in x from x equals a to x equals b. Then the volume of solid of revolution formed by revolving R around the x-axis is given by. Note that the integral involving the inner radius represents the volume of the whole and is subtracted from the integral involving the outer radius. Find the volume of a solid of a revolution formed by revolving the region bounded below by the graph of g of x and above by the graph of f of x for an interval in x from x equals 1 to x equals 2 around the x-axis. Revolving the region about the x-axis generates a solid of a revolution with a cavity in the middle. Look at the figure. This illustration clearly shows what is happening. The integral involving the inner radius represents the volume of the inner cylinder, that is, of the hole. When the volume of the inner cylinder is subtracted from the outer cylinder, we get the requested volume in this example. We now calculate the integral to find the volume of the resulting solid of a revolution. Find the volume obtained by rotating the graphs of g of x and f of x around the y-axis. First, we will graph our boundary region and then we determine where the two curves intersect. Revolving the region about the y-axis generates a solid of revolution with a cavity. Cross-section is perpendicular to the y-axis, so we should solve the equations for x. As we can see, the limits of integration do not change. Look at the figure. When the volume of the inner cylinder is subtracted from the outer cylinder, we get the requested volume. We now calculate the integral to find the volume of the resulting solid of revolution. Find the volume of the solid formed by revolving the region bounded by the graphs of f of x, y equals 0, and x equals 1 about the y-axis. Since the axis of revolution is vertical, we must integrate with respect to y, not x. So we must solve the equation for x. Revolving the region about the y-axis generates a solid of revolution with a cavity in the middle between y equals 1 and y equals 2. From y equals 0 to y equals 1, the solid is a cylinder of revolution. The cross-section is a circle, and the radius is equal to 1. So we calculate its volume using the slice method. In fact, we can see a right circular cylinder of radius 1 and height 1. This part of the volume could have been determined without using calculus, but we are in a course of calculus, so we will use calculus to find this volume as well. From y equals 1 to y equals 2, the solid has a hole in the middle, so we use the washer method. The outer radius is equal to 1, and the inner radius is given by the equation for y. We will find the two volumes and then sum them up to obtain the total volume of this solid. Find the volume obtained by rotating the graphs of f of x and y equals 12 on the interval from 0 to 3 about the line y equals 15. First, we will graph our boundary region. When the graph of f of x rotates about the line y equals 15, it generates a washer. The inner radius is 3. The outer radius of this washer is the distance from f of x to the line y equals 15. The outer radius is 15 minus f of x, rather than f of x minus 15, because the line y equals 15 lies above the graph of f of x. We now perform the calculations.